When So when we talk about our reactions, as you very well know, we have certain reactions that are known as reversible reactions. When we talk about reversible reactions, so they are reactions that can go forward and backwards, meaning that your reactant can turn into the product and product can turn into the reactant, right? A very simple example of these kind of reactions that you guys would have already covered in your IGCSE is, for example, there are multiple reactions. You can have Haber process, which is going to be nitrogen plus hydrogen is giving us ammonia. Or you guys can have your contact process, which was sulfur dioxide plus oxygen gives us sulfur trioxide, right? Or hydrogen plus iodine gives us hydrogen iodide, right? Or if you're going to go ahead and you're going to talk about it, another reaction you guys studied in IGCSE was this. Your two molecules of nitrogen oxide can dimerize to give you N2O, right? So these are all reversible reactions. They all have this is the sign of a reversible equation. When we're going to go ahead and talk about it, so the concentration, initially, the concentration of the reactants is high and the products are zero, right? Initially, at the start of the reaction, of course, you will only have reactants and no product. As the reaction proceeds, the reactants are converted into products, right? So as the reaction proceeds, your reactants are converted into products. As the concentration of the product increases, they start to turn back into reactant. This continues until the rate of the forward reaction is equal to the rate of backwards reaction. This point is known as dynamic equilibrium, right? So this is known as equilibrium when the rate of forward reaction is equals to the rate of backward reaction. I'm sure this is something you guys have already studied. Now, there are three specific features, or there are three features of dynamic equilibrium. So there are three features of a dynamic equilibrium. Three features of a dynamic equilibrium are that number one, the backward reaction and the forward reaction. Occur simultaneously. Point number one. Point number two, the rate of forward reaction is equal to the rate of backward reaction. And point number three is that the concentration of product and reactant is constant at equilibrium. What does that mean? Please keep in mind that doesn't mean that the concentration of the product and reactant are equal to each other, because students have made that mistake. This doesn't mean that the concentration of product and reactant is equal. It simply means that the concentration of product and reactant is constant, right? It's constant, meaning that if I'm getting 2 mole per dm cube of the product, so as the reaction proceeds, I will keep on getting 2 mole, 2 mole, 2 mole, 2 mole. It will seem like it's stationary. The same like the reaction is not happening because I'm constantly getting the same amount of product or the same amount of reactant. Since I'm getting the same amount of reactant in product, you guys might even think, okay, maybe is the reaction not happening? Why is the product not increasing? But the reason the product is not increasing is because you have reached a state of dynamic equilibrium, right? So at whatever speed I'm making the product, that product is quickly breaking down to become the reactant. So whatever speed or whatever is the rate of the forward reaction, the rate of the backward reaction is the same. So as quickly as the product is made, just as quickly it is broken down. So it seems like you are at an equilibrium. You are at a constant value. Then, if you're going to go ahead and draw a graph, so the graph is going to look like this. First of all, on the y-axis, we're going to have concentration. Just simple concentration, not concentration of product or reactant. Then on the y-axis, x-axis, you're going to have your time in seconds. Your graph, when you're going to go ahead and draw it, it's going to look like this. Let's first draw the graph of reactant. So the graph of reactant is going to show you something like this, right? The graph of the reactant, as you can see, it is decreasing. Why is the concentration of the reactant decreasing? Because the reactant is getting used up to make the product. You will see that the initial rate of reaction is high. Why is the initial rate of reaction high? Because we have a lot of reactant. In the start, we have a lot of reactant and not enough product. So the reaction takes place very quickly. Then we have our product. The concentration of the product increases until it also becomes constant. Right? Again, you will see that the initial rate of reaction is high. And this particular point is what our dynamic equilibrium is. Now, so this is what the graph is going to, this is what the graph may look like. One of the ways of what your graph can actually go ahead and look like. So, this is an example of what you might see. So, when we go ahead and talk about it, another important property that we need to understand related to our dynamic equilibrium is that dynamic equilibrium is established in a closed system, meaning that you need to make sure that your vessel is a closed vessel. Okay? If your vessel is an open vessel, so for example, if I'm doing nitrogen plus hydrogen gives us ammonia. Let's say I do it in an open container. What will happen? Ammonia is a gas. As the reaction is going to proceed, my gas is going to slowly escape. As my gas is going to escape, so what's happening? The product is being lost. Since the product is being lost, so the backward reaction will not be happening. So there will be no dynamic equilibrium. You will never reach the point of dynamic equilibrium. Why? Because all the product has been lost. So it's very important that the dynamic equilibrium is established in a closed system. You cannot establish it in an open system. Then dynamic equilibrium is affected by a few factors. Factor number one that we're going to take a look at is pressure. Factor number two that we're going to go ahead and take a look at is temperature. And finally, we are going to take a look at catalyst as well. It might not have an effect if you remember your IGCSE, but we're going to still discuss catalyst just for the sake of revising what we're doing. Now, so we are going to now take a look at all of these three factors individually one by one. Now, when we're going to go ahead and talk about it, so let's do factors affecting dynamic equilibrium. The factors that are affecting dynamic equilibrium, before we can discuss this, we need to discuss a principle. Now, this principle, I'm not sure if you guys have covered before or not. I'll go over it with you guys. If you guys already know it, you can even say it that, Miss, we have studied this before, we know what it is, it's okay. So let me know. This I'm not sure if you guys know or not. But there is a principle that we have that is known as Le-Chatelier's principle, right? Now, when we go ahead and we talk about Le-Chatelier's principle, what did we say? Le-Chatelier's, I think this is the spelling, principle. So when we talk about Le-Chatelier's principle, just give me 1 second. So when we talk about Le-Chatelier's principle, what actually is Le-Chatelier's principle? Okay, Le-Chatelier was basically a French chemist, and he studied how these different factors affect the position of the equilibrium. So he said, if one or more factors affect an equilibrium, one or more factors that affect an equilibrium is changed, the position of the equilibrium shifts in the direction that opposes the change. What does this statement even mean? Before we talk about what this statement mean, let's start with pressure. I will explain the effect of pressure, and as we talk about the effect of pressure, it will make sense to you guys what this guy is actually trying to say. So let's talk about the effect of pressure. First, let me write down the statements for you guys. What is the effect of pressure, right? And then I will explain it. Point number one, if we increase the pressure, the equilibrium shifts to the side with less number of molecules. Point number two, if we decrease the pressure, the equilibrium shifts to the side with greater number of molecules, right? And I will explain to you guys how this fits in with Le-Chatelier's principle. What's the theory behind this? If the number of molecules on both sides are equal, or if the number of molecules on both sides are equal, or if the reactants and products are not in gaseous state, pressure will have no effect. Right? Now, I said when we increase the pressure, the equilibrium shifts to the side with less number of molecules, meaning that if this is my meaning that if this is my equation, we were discussing the ammonia equation, so let's just continue with that, make things simple for you and me. So in the ammonia equation, this was the equation that you and I had studied, right? Nitrogen plus hydrogen, both of these would be gaseous, react to give us ammonia. Now, over here, if you're going to go ahead and take a look, so what are we going to see? We're going to see if we increase the pressure, the equilibrium shifts. The equilibrium is going to shift to the right hand side, and the yield of ammonia increases. Why is it shifting to the right hand side? The reason it is shifting to the right hand side is because on the right hand side, the molecules are less. On the left hand side, we have four molecules, three of hydrogen and one of nitrogen. On the right hand side, we have two. So when we increase the pressure, the equilibrium shifts to the side with less number of molecules. So in our case, it's going to shift to the right side. Now, why does this actually happen? Now, think of it this way. Whenever we change any of these factors, we're studying three factors or two factors, pressure and temperature. Whenever we change these factors, what happens? What happens is that it disrupts the equilibrium that has been established. The reaction tries to restore the equilibrium. The reaction tries to bring back the equilibrium. So we have, by increasing the pressure, you and I have disrupted the equilibrium. The reaction will say, okay, listen, we were at equilibrium, we were going great, but this has been disrupted. We need to somehow bring back that equilibrium. We need to restore our equilibrium. What we have done is that we have increased the pressure. So the reaction is going to try to decrease the pressure and bring it back. So the reaction restores or goes back to the equilibrium state. For the reaction to go back to equilibrium state, so the reaction will say, listen, we need to somehow decrease the pressure. How can the reaction decrease the pressure? It will say, why don't we shift to the side with lesser number of molecules? Why? Lesser number of molecules means lesser collisions. Lesser collisions means lesser force per unit area, which is what pressure is. Pressure is force per unit area. Lesser force per unit area, so less pressure is exerted by the gas. Less pressure is exerted by the gas. As a result, the pressure will reduce and it's going to come back to the equilibrium state. It's going to restore the equilibrium. This is what Le Chatelier was saying. That if we change these factors, the position of the equilibrium shifts in the direction that causes the change. So if the change is to increase the pressure, the equilibrium will shift in the direction that will oppose it, that will decrease the pressure. This is Le Chatelier's principle. And this is the theory and the logic as to why this is actually happening, right? Excuse me, guys, I'm sorry. So this is what is actually happening, right? Then when we are going to go ahead and we are going to talk about it. So if we decrease the pressure, the equilibrium shifts to left hand side, right? And now you and I can understand why. The reason it's shifting to the left hand side is because we have decreased the pressure. We have again disturbed the state of equilibrium. The reaction will try to restore the equilibrium. The reaction will try to bring that equilibrium back. So to bring that equilibrium back, it needs to increase that pressure. How will it do that? It will go to the side with more number of molecules. More number of molecules means that there will be more collisions, more force exerted per unit area, and as a result, pressure will increase and your equilibrium will be restored, right? So this is what we had to go ahead and we had to discuss about pressure. Then let's go ahead and talk about temperature. Well, we're going to go ahead and talk about our second point, that is temperature. Now, when we talk about temperature, so what is the effect of temperature? Point number one, if we increase the temperature, the reaction shifts to the endothermic side. If we decrease the temperature, the reaction shifts to exothermic side. What does that mean? That basically means that, and we will see how this fits in with your Le Chatelier's principle as well, right? What this basically means is that let's say that we have our reaction where our hydrogen, this is our reaction, right? And of course, it has to be gaseous state. So let's say that our delta H over here is going to be what? It's plus 9.6 kilojoules per mole. Now, what is going to happen? If we increase the temperature, the reaction shifts to the right side. Why does it shift to the right side? Because the right side is the endothermic side. Remember this, the value that they have given you for delta H is always, always, always for the forward reaction, right? So this plus 9.6 kilojoules per mole is the value for the forward reaction. Automatically, it's understood. It's understood there that the value of delta H given to us in the question is always, always about the forward reaction. So the forward reaction is endothermic. Okay, we can even note these points down that the forward reaction is endothermic. So whatever the forward reaction is, the backward reaction is opposite. So the forward reaction is endothermic. That means the backward reaction is exothermic. So if we increase the pressure, the temperature shifts to the right side. And if we decrease the temperature, the reaction shifts to left side. Now let's understand why this happens based on Le Chatelier's principle. Le Chatelier's principle, so when we increase the temperature, we have disrupted the equilibrium. Chatelier said that the reaction will shift in such a way that it will oppose the change that is happening. So what is the change that is happening? Temperature is increasing. The reaction has to shift in such a way that it can oppose the increase, meaning that the reaction has to shift in such a way that it can decrease the temperature. So it will shift to the endothermic side. Why? Because endothermic reaction absorbs heat. So if the reaction is going to shift to the endothermic side, the reaction is going to start to absorb the heat from the surroundings and the temperature will decrease and the equilibrium will be restored. If we decrease the temperature again, according to Le Chatelier, we have to oppose it. We have to increase the temperature. So the reaction shifts to the exothermic side. The exothermic sides will start to produce heat energy. Exothermic reaction will start to release heat energy and the temperature is going to increase and the equilibrium will be restored. Final factor that you and I need to go ahead and take a look at is, actually I mentioned catalyst, but catalyst doesn't have an effect on position of equilibrium. We actually have to discuss concentration. So when we're going to go ahead and we're going to talk about it, what are we going to see? If we increase the concentration of the reactant, the equilibrium shifts to the right side. And if we decrease the concentration of the reactant, the equilibrium shifts to left side. Why does that happen? Again, how are you guys going to explain it? Using the Lee-Chatelier principle. According to the Lee-Chatelier principle, so if I'm increasing the concentration of the reactant, I have made too much reactant. Lee-Chatelier principle means that we need to oppose it and we need to bring that value back down. So how are we going to bring that value back down? The reaction will shift to the right side, meaning that the reaction will go forward, meaning that your reactant will start to convert into product. As your reactant will start to convert into product, so the concentration of reactant will decrease and it will come back to equilibrium. If we decrease the concentration of reactant, so now we have again made a change. We have the reactant is too less, right? So the equilibrium has to go in such a way that it opposes the change. It goes opposite to it. It needs to increase the concentration of the reactant back up. So how will it do it? By shifting to the backward side or the left side. In the backward reaction, the product will break down and give you the reactant. So the amount of reactant will increase and equilibrium will be restored. Now this was about concentration of reactant. What about concentration of product? If we increase the concentration of product, the equilibrium shifts to the left side. And if we decrease the concentration of the product, the equilibrium shifts to the right side. Again, same principle. If I decrease the concentration of the product, so if I increase the concentration of the product, the equilibrium will go to the left side. The reaction will go backwards. Why? Because we have too much product. According to Lee-Chatelier principle, the reaction has to shift in such a way that it can oppose the change. So the change is increase in concentration. To oppose it, I have to decrease the concentration. How can I decrease the concentration of the product? Make the reaction go backwards. Turn that product back into the reactant, right? Similarly, if my product is too less, the equilibrium will go to the right side. Why is it going to go to the right side? Because I need to go ahead and I need to increase my concentration of product back to normal. So my reaction is going to go forward so that the reactant is converted into the reaction is converted into product and the amount of product increases. Finally, and the last thing we are going to discuss is the effect of catalyst. So when we're going to go ahead and talk about it, catalyst has no effect on the position of the equilibrium. Why? Because it increases the rate of forward and backward reaction equally. Catalyst increases the speed of reaction. It most definitely does. That is why we need a catalyst for a lot of things. For example, in Haber process, we were using iron as our catalyst, right? In contact process, we were using vanadium 5 oxide. So in a lot of these reactions, we require a catalyst. A catalyst will increase the speed of reaction. It will increase the rate of reaction. But it will increase the rate of both forward reaction and backwards reaction. And equally, it won't increase one more or one less. It will increase both of them and it will do it equally. So there is no overall effect on the position of the equilibrium. Now, this is all making sense. We understand the basic concept of how our dynamic equilibrium works. What is the effect of concentration, pressure, and temperature on the position of equilibrium, and we understand Lee-Chatellier's principle. Right? Does anybody have any confusion in this portion of the topic?
No.
Aruj, is everything clear? I'm sorry I went over it a bit quickly because this is something you guys have done before in your IGCSE as well. So but if there's anything that you guys have forgotten or anything that you guys want me to go over in more detail, then you guys can let me know. Aruj, is everything clear? I hope there's no confusion.
Yes, yes.
Okay, all right. Now this is done. So this was something that was more of something you guys had done before. Now we are going to go ahead and take a look at the actual portion of the topic that is something that is going to be new for you and something that you guys have not done before. Okay, what we are going to go ahead and talk about is we are going to talk about something that is known as your equilibrium constant. Now, when we talk about equilibrium constant, so equilibrium constant is basically there are two equilibrium constants that we have to study. Equilibrium constant of concentration and equilibrium constant of pressure. We will start by studying the equilibrium constant of concentration. So let's go ahead and take a look. Okay. Now, equilibrium constant is a constant. It's basically a constant, right? That we can use to figure out the concentration of the products and the concentration of the reactants. Now, first thing is first, let's take a very simple equation in front of us. The equation you and I are going to go ahead and take is this. We have got hydrogen. This hydrogen will react with iodine to give us hydrogen iodide. Right? Now, if you guys decide to run an experiment, for example, you guys said, okay, what is the concentration of hydrogen and iodine at the start of the reaction? Of course, the product will be zero. At the start of the reaction, you don't have a product. So, what is the concentration of hydrogen and iodine at the start of the reaction? You noted that down, right? Then you let the reaction proceed for a little while, and after a little while, you went ahead and you wrote down again, you measured the concentration of hydrogen, iodine, and hydrogen iodide. And you kept on repeating the processes until you reached a state of equilibrium, right? Once it reached a state of equilibrium, so you can actually go ahead and calculate the equilibrium constant. The equilibrium constant will show you the relationship between the concentration of the products and the reactants, right? Equilibrium constant will allow you to calculate or allow you to measure or give you an idea of measuring the rate or relationship between the product and the reactant. Now, the symbol for equilibrium constant is Kc. We write down Kc. Okay. K is the symbol for equilibrium constant, and we write down C to show that this is the symbol of concentration. So the C shows us that the symbol is for concentration because we also have the constant for pressure. So we will study that as well. So K means equilibrium constant and C means concentration. Now, there is a formula for Kc that you guys need to know. The sad thing is that there is no fixed formula. You guys will have to figure out the formula each and every time by yourself. The good thing is that it's not hard to figure out. We will do concentration of the product. Whenever you're writing down concentration, remember to put square brackets. So this is my product and the concentration of the reactant. So let's take this equation and let's practice how we can make our equilibrium constant expression, the expression for equilibrium constant. So the equilibrium constant expression can be made in such a way. My product is hydrogen iodide. I will write down small brackets and I will write down hydrogen iodide. My reactant, I have two reactants, hydrogen and iodine. Now, after you have done this, you need to also take a look at the mole ratio. Can you see that we have 2 is the mole ratio of hydrogen iodide? We have 1 of iodine and 1 of hydrogen, but 2 of hydrogen iodide. So, where am I going to put this 2? I am going to put it as the power, which means hydrogen iodide square divided by hydrogen multiplied by iodine. I don't have to worry about the power of hydrogen and iodine because their mole ratio is 1. But for hydrogen iodide, I will have to square it. What if we change the equation? What if we have N2 plus 2 3H2 gives us 2NH3? What now? Again, if you want to make our equation, we will do product over reactant. Our product is going to be NH3 ammonia square brackets NH3 divided by the 2 reactants nitrogen multiplied by hydrogen. Now let's take a look at the mole ratio. The mole ratio for NH3 is 2, right? So I will write down NH3 raised to the power of 2. The mole ratio for hydrogen is 3. So hydrogen will be raised to the power of 3. It will be Q. For nitrogen is just 1, so we don't have to write it down. So this is how you're going to go ahead and figure out the value for equilibrium constant. So every single time you guys will have to figure out the expression by yourself. But like I said, the good thing is that it's not complicated to figure out the expression. You just have to do product over reactant, and whatever mole ratio is written in the question, you will simply use that to add the powers, right? Let's say that we had 2SO2 plus O2 gives us 2SO3, right? To figure out the Kc, all you have to do is product over reactant. Our product is SO3. Our reactant is SO2 and O2. So SO2 will be raised to the power of 2. SO3 will be raised to the power of 2 because it has a mole ratio of 2. SO2 will be raised to the power of 2. And oxygen will only be raised to the power of 1, right? We don't need to worry about the power of oxygen because the mole ratio of oxygen is 1. So that's the first point. You guys will have to figure out your expression for Kc by yourself. Each and every time you will have to figure out the value for or the expression for Kc by yourself. Once you guys have figured the expression, the rest of it is, well, it's not simple, but the rest of the process is you need to take the concentrations, put them in the formula you have just made, and calculate. Keep one thing in mind. Concentration should be taken at equilibrium. Now, in a little bit, or maybe in next class, I don't know, but in this topic, we are going to see that oftentimes, in fact, majority of the times in your past papers, they will not give you the value of your the concentrations given to you are not at equilibrium. They will give you initial concentration. So concentration at the start was this. Then for one of the reactants or one of the products, they will say, oh, concentration at equilibrium was this. Before you guys can solve the question, you will have to figure it out. You guys will have to solve it and get the values of concentration at equilibrium for all of them. This formula is for equilibrium concentration, not for initial concentration, not for 10 seconds later, not for 20 seconds later. The concentrations at equilibrium, that is what we need. So we will learn how we can actually calculate the values of expression at equilibrium. But we will go over that, that's no problem. But the point I wanted to emphasize for you guys was that what the concentrations have to be at equilibrium. Do not use initial concentration, do not use any of the middle concentration. We need the concentration at equilibrium to solve our question. Second point, you will have to unit the unit. The unit is not fixed. You will have to, just like you have to figure out the expression or the formula each and every time, you guys will also have to figure out the unit each and every time. If the question comes in paper 2, then your answer is incomplete without the unit. Please note that. If the question comes in paper 2 and they ask you to calculate the value of Kc and you guys write down the numerical value and you don't mention the units, they will deduct marks for it. Because calculation of units is very important, because over here the units are not fixed. The units are different depending upon what the expression is. For example, our first expression over here is that hydrogen iodide square divided by hydrogen iodine. So when we're going to go ahead and take a look, hydrogen iodide, what is the unit for concentration? Mole per dm cube. So you write that down. Now over here, in this particular case, this question or this expression is easy. Why is it easy? Because everything cancels out. At the numerator, we have mole in dm cube minus 3 squared. At the denominator, again, we have mole dm cube, mole dm cube. So this is actually also getting squared. So in this case, we can cancel it out and the value of Kc will have no units. So in this case, if yeah, by the way, I'm not saying that every time a unit is must. Sometimes the unit will get cancelled out. So the value of Kc, you might just be getting a numerical value. Sometimes there might not even be a unit associated with it, right? So in this case, the value of Kc is getting cancelled out. There is no unit left. So if you write down just the numerical value, it's 100% correct. They will not have marks for that because it actually does not have any units. But please don't just randomly guess it. Solve the question, figure out if Kc has units or not, and then go for the calculations, right? Let's take a look at the next one. The next one that we have is, we have ammonia raised to the power of 2 divided by nitrogen and hydrogen. So nitrogen, again, ammonia, the unit is going to be mole per dm cube squared divided by mole dm cube, and for hydrogen, mole dm cube, and this will be raised to the power of 3. Now, if you guys have done the topic of indices in IGCSE Maths, if you guys have done IGCSE Maths and you've gone over your power, the topic of indices, this will be easier for you guys to solve. So, mole dm cube minus 3 raised to the power of 2 divided by, over here, whenever we are multiplying two indices, we add them up. So this is raised to the power of 1. Whenever we don't write down the power, it automatically means this is power of 1. So 3 plus 1 becomes 4. So mole dm minus 3 raised to the power of 4. Over here, these two cancel out. We can divide, right? So we end up getting 1 divided by mole dm minus 3 squared, right? Because this is square and this is 4. Right? Whenever we are doing our indices, so whenever we are dividing, we subtract the powers. So if I do 4 minus 2, I get 2, right? So my unit, I can either write it down as 1 upon mole dm minus 3, or I can write it down as mole minus 1, or I can write it down as, sorry, as mole dm minus 3 raised to the power of minus 2. Right? You can either write it down like that, or you can write it down as 1 upon mole dm cube. whatever you like, you can go ahead and write down as your unit, right? You can rearrange the formula, doesn't matter. Your unit, this is your unit, right? So as you can see, the unit is going to change depending upon what your product is going, depending upon your formula for equilibrium concentration, right? For example, if you take a look over here for the sulfur trioxide one, so this is going to be mole dm minus 3 squared divided by mole dm minus 3 square multiplied by mole dm minus 3. So in this case, when you're going to go ahead and you're going to talk about it, this is going to end up becoming, what is this going to end up becoming? This is going to end up becoming, hold on one second. This is going to end up becoming mole dm minus 3 squared divided by mole dm minus 3 cubed. Why? Because we add up the power. So 2 plus 1 is 3. So when you're going to cancel it out, or when two powers are dividing, what do? We subtract the powers. So 3 minus 2 is 1. Or if you want to take it, bring it up to the numerator, then you will do 2 minus 3. So your answer is going to come out mole dm minus 3 raised to the power of 1. So mole upon dm, right? Raised to the power of minus 1. Right? So this is how you guys are going to figure out the unit. So every single time when you guys are doing these questions, you have got a few things that you guys will have to do. Every single time you'll figure out the value of Kc yourself. It's not going to be given to you. You guys will have to figure out the equilibrium constant by yourself, right? Not only will you guys have to figure out the equilibrium constant by yourself, but you will also have to figure out the you will also have to figure out um the what do you call this the unit, right? Both things are up to you. Both things are completely up to you guys. You will have to go ahead and figure them out yourself. Please don't forget when doing especially your paper 2 questions, because in paper 1 it's mcqs, right? So unless they have specifically made the question about units, maybe you can get away without doing the unit part. But for paper 200%, you guys need to make sure each and every time you also calculate your units as well. So this is what your Kc is. Kc gives you the relationship between your um, between the concentration of your reactants and products, right? And we can use this particular process, or we can use these calculations to go ahead and figure out the value of Kc. And we will also remember that each and every time we have to also go ahead and we have to do what? We also have to make sure that we are um, calculating the units, right? Now, let's go ahead and take a look at a few and at like a question. Let's just go ahead, and you and me, let's just take a question and let's see how we are going to go ahead and do this particular questions. Now, like I said, majority of the questions are going to be dealing with they'll give you the initial concentration, and then they will say, oh, can you calculate? Then you have to calculate first the concentration at the equilibrium, and then you solve the question. But I'm not going to go over that right now. First of all, let's just take a very simple question, right? Now, the reaction is like this. Ethanol reacts with ethanoic acid to form ethyl ethonate. The reason I've selected this reaction is because this is the reaction where the alcohol and carboxylic acid react together to make an ester. So you guys might remember from IGCSE that it was a reversible reaction, right? So ethyl ethonate and oh yeah, we also get water. Now 500 centimeter cube of the reaction mixture reaches equilibrium and contains 0.235 moles of ethanoic acid and 0.182 moles of ethyl ethonate and also 0.182 moles of water. Use this data to calculate a value of Kc. Now, first step in these questions that I want you guys to do is if the equation is not given to you, please construct the equation. If it's provided to you, all well and good. If it's not, please make sure you always start by constructing the equation. Now, we have not gone over organic chemistry yet. You might remember this ester reaction from last year. But if you guys haven't, we haven't gone over organic chemistry yet. When we do, I will expect you guys to be able to make these equations. But right now, I'm going to make it for you guys because, like I said, you guys haven't gone over it. So ethanol reacts with ethanoic acid and this gives us ethyl ethonate plus water. Now, when we are going to go ahead and we're going to talk about it. So over here, what are we going to go ahead and do? Okay, hold on one second. I did not write down the question. I forgot to add the moles for ethanol. Okay, ethanoic acid. And for ethanol, let's just go ahead and take 0.035. 0.035 moles of ethanol. Right? Fine. So what you guys are going to go ahead and do is that step one, you're going to make sure all the concentrations you're using are at equilibrium. In this question, they have already given us the values at equilibrium, so that makes situation easy for you and me. We don't have to worry too much about it. So our otherwise, if they haven't given you an equilibrium, so you guys are going to make a proper table. You're going to write down initial. You're going to write down the equation, then initial, and under the initial, what values are given. Then equilibrium, then what values are given, and then you will do a calculation, which I will teach you how to do. But every time, make sure you write it down exactly like this. It's just for the sake of practice. Once you guys do it like this, you guys make sure that you don't do any mistakes, right? So we have 0.035 mole of ethanol, 0.235 mole of ethanoic acid. We have 0.182 mole of ethyl ethonate and 0.182 moles of water as well. Now, first thing that you guys want to go ahead and do is that you want to make sure that you calculate the concentration. Why? Because this is equilibrium constant for concentration. If you don't have the concentration, right, then how are you going to do calculations? You need the concentration. So we cannot use the moles directly as it is. We will have to calculate the concentration at equilibrium. The volume is 500 centimeter cube. So we will use the formula concentration is equals to moles divided by volume and find out the concentration. Remember to convert your centimeter cube into dm cube. Right? When we're going to go ahead and do that, we're going to end up getting our value as 0.47. mole per dm cube. We will get 0.070 mole per dm cube, right? We will end up getting 0.364 for both of them. Now, next step is to make the expression of Kc. Kc is product over reactant. Product is CH3, COO, C2H5, and H2O divided by C2H5OH multiplied by CH3COOH. Write down all the values that we have just calculated. 0.364 multiplied by 0.364 divided by 0.47 divided by 0.07. When you guys are going to put all the calculations, your final answer is going to come out as 4.03. Now, are we done? No. We need to worry about the units. For the units, again, I have mole per dm cube and I have mole per dm cube. This is divided by the concentration of our reactants. So both of them will be in mole per dm cube. So in this case, as you can see, the units cancel out. So there will be no units. So the value of Kc is simply 4.03. And this is how we're going to go ahead and do our calculation. Making sense, guys? Understand how we're going to be using our calculations and how we're going to be getting the answer?
Yes.
Aruj, making sense? No confusion?
Yes, miss.
Okay, all right. Okay, guys, then we're going to go ahead and stop it over here for today, and we will continue, inshallah, with the topic in the next class. All